Okay, so we're talking about equations and how they produce sets of numbers. But I want, and the last example was, well, these examples show you how in how many ways it can happen. So it might be one equation might produce multiple answers. So then you are forced to speak of a solution rather than the solution because you could expect multiple answers. So how do you make a solution one and only? You combine all these solutions, all numbers together, and that is a set, and we call it the solution set. Okay, so that's what makes it worthwhile, especially if you speak of if you want one answer. Well, that's the answer. The answer is the set of all solutions. Is what you were expected when you were solving an equation. But this was only introduced until a bit early, equations, until we have enough functions. We can't really talk a lot about equations. So we have just a few functions right now that we are ready to talk about, and there will be a lot more. This time it's just they introduced in order to illustrate sets. Okay, so these are sets of numbers, and as you can see, we have the possibilities are not large just yet. So I want to go back to this example and look at equations for different functions. Okay. So I go back to this example of boys and balls. Okay. So let me remind you that we are talking about so two sets, x and y. Okay. The name of the function is f. So the codomain is y, the balls. Okay, so we could number them or not, but this is the which ball each boy prefers. Okay, so then so we have visualized it already, but the question that might be asked is to try to reverse these things. So for example, this is the data that you're supplied with, and the question might be, for example, which boys prefer to play basketball? What's the answer? You got to point out the answer. What's the answer? Tom and Bill. Tom and Ben. So the answer is not Tom. The answer is not Ben. The answer is Tom and Ben. Okay. Similarly, the answer who prefers to play football. The answer is Sid and Ken. Okay. So in other words, the answer is once again a set. Okay, so in fact it is you could see an equation. So let me try to visualize of what. Well, here's the equation that we're trying to talk about at the bottom. Say I have my function f of say x. So x is capitalized the set, but here x stands for a boy, f stands for this function, and it is equal to say football. Okay, so what we're looking at is an equation. So just the same exact language as we have used for numbers that we use for anything else. So equations don't have to be about numbers necessarily. So that's a typical equation. So a function is given, specific function, even though there's no formula, but it is as specific as it gets. And then you have an equation. So for you're supposed to find all x for which f of x is equal to a particular value. So in this particular case, it's basketball. And so the answer is, the solution set is Sid Can. Okay. And then you can start with any of the three or any of the four outputs. Right, so the outputs are those four, and you can ask the same question. So let me move it out of the way. So let's do that. So the other question, the other equation that I want to solve is f. Oops, that's thick. Okay, f. Okay, that's good. F of x is equal to baseball. What's the solution? None, so empty set. By the way, there is another way the notation for the empty set is like this. Okay, for the empty set. Remember, the answer ideally when you the answer is presented in the form of a list. Okay, so as I just did with the previous equation. Okay, and then if that and then what you got in the next line is a list with no entries. Okay, so you just have two braces with nothing inside. So that's quite descriptive of what we're trying to say. So there is nothing there. So even though we have a list, there are no items on the list. Okay, so since we started with this, let's just solve all the possible equations that are available. So moving up, I have my tennis here. Okay, so the solution is net, okay, 1. So even though there's only one answer, I still put it in brackets to indicating that this is the solution set, and I have found it. Okay, and finally, the basketball, f of x is equal to basketball, and the answer for x is Tom and Ben. All of these are subsets of x, by the way. Okay, so I'm starting on the over here with element of y elements of y are here, right? So I pick one at a time, and then I'm looking for elements of x. Okay, so these are elements of x. Well, they are supposed to be. I haven't found them yet. But on the right, then I do find them in the form of sets, and once again, they are all subsets of x capital. Okay, so with numbers, it's exactly the same story. It's just the two sets would be all numerical, but they could still be two different sets. Okay, so this gives us an important opening point for the following. It is called the set building notation. Which can be expressed as follows: x satisfies a condition. Okay, so then, for example, x such that f of x is equal to basketball. So that equation is a condition. You could call it condition, restriction, equation. Well, the condition could be equation, it could be something else. But this is an example of a set building notation. So what I'm saying here is all x's that satisfy the equation. Okay, and the answer is then this x is, as we have discovered, is what is it for the basketball is Tom and Ben. Tom, Ben. So this is once again the solution set. The solution set. The solution set of an equation can now be written in this fashion. So once again, all x's that satisfy the equation. And once again, we talked about that last time. What it means to satisfy an equation or satisfy a restriction is simply you can just go one by one, plug it in, and see if it satisfies. Okay, and it is especially typical when you do it with numbers, but same with anything else. So we take Tom and Ben. We take Tom, plug it in for x. Look up in our diagram. Look what does Tom prefer. And the answer, Tom prefer basketball. Okay, yes. So we picked put Tom on the list. Then move on to Ben. What does he like? He likes basketball. So once again, I'll put it on the list. Ned, he likes tennis, which means that he's not on the list. Ken likes football, and Sid likes football. So they are once again not on the list. And so that's how we get this answer. And you can continue on in that fashion indefinitely. So this is once again set building notation, and you can certainly, even about such a simple function, you can ask many questions and impose different restrictions on the sets. It doesn't have to be an equation, and it could be, for example, if I'm looking at my set, I could create a set of, say, all boys who wear red shirts. Okay, and that set will consist of a single person. That's net. Okay, or I could look at the set Y and say, how about this? How about this? So X, it's rather Y. So I'm talking about balls this time. Y is round. So these are balls. These were boys. Okay, and we just look at it. So this second one has nothing to do with the function itself. We're just looking at these 4 balls, and we pick those according to the restriction, those that are round, which means that what is the answer?
Basketball, maybe it's baseball, tennis.
Basketball, but not football. Basketball, tennis, and baseball. So that's once again set building notation. So it is important once again to go back and remember what we meant by sets, and those are just a bunch of elements. The only requirement is that it should be unambiguous about whether or not a particular element does or does not belong to the set. So if there is a condition that if that condition is unambiguous, we have then created a set. Okay, so ball being round, let's say, is an unambiguous condition. So then we will always know whether or not ball doesn't belong to the set, because we know whether or not it is round. With the first example, once again, we know which assuming that every boy prefers one single ball game, which means that once again we will know if we examine everything, we will know what that set consists of. So it means that you are sort of the first what's you have on the left here is sort of a question that you may or may not be able to answer with what's on the right. Okay, so you can impose a condition, and then you work it out and find out what all of the elements of a bigger set that satisfy that condition. Okay, so but the basic idea is to start with set building notation. So ahead of time, you don't know what it's going to be. Can you simplify it to such a degree that you end up with nothing but a list? Maybe not. We're going to see that it's not always possible. In fact, let's switch back to numbers, and let me remind you that say I have this set. So now numbers. X squared is equal to 1, and the answer is it's an equation. We are speaking of a solution set. We could simplify it easily and write the answer as a list. What is that list? 1 and -1. Okay, by the way, it's the same as -1 and 1. The order doesn't matter really when you have a list. I mean, you are certainly welcome to put it in the increasing order, but it's not necessarily required. Then you have, once again, for quadratic equation, you can have 0, 1, or 2 solutions typically. And then you could have, once again, x squared is equal to -1. As far as real numbers are concerned, there is none. But here's another one. A bit trickier. What about this one? What? Give me the set. This set, you remember what it is. Give me all x for which x is equal to x. That's right. That's right. So in other words, every number satisfies this property. Okay. So all numbers are good. In fact, it don't have to be numbers. I mean, you say you can try to impose a restriction like that is on say boys, and once again the restriction is not really a restriction. X is equal to x. How about this one?
Only one?
No. No. What x's satisfy this restriction? Okay, let me give you two. Okay, can you solve either one of these? So x's that satisfy the restriction that 1 is equal to 0, and then the other one, x's satisfy the restriction that 1 is equal to 1. Well, let's start from the top. Does 2 satisfy the restriction that 1 is equal to 1?
Just be 1.
What?
Would it just be 1?
No. No, once again, go one by one through all numbers. Start with any. You can start, say, start with 0. So if x is equal to 0, x is equal to 0, does x equal to 0 satisfy 1 is equal to 1? Well, question mark. Yes. Why yes? There is no x there. There is no x to begin with, but not that you know, the left line is 1 is equal to 0. It also doesn't have x there, and yet the answer will be different. So it actually matters that that restriction we're looking at, is it satisfied or not satisfied? Is it true or not? Which one? So this is true, and this is false. It doesn't matter what x is. The first one will always be true, and the second will always be false. Okay, so if for the first one, it doesn't matter what x we pick, the condition will always be satisfied. Which means the what? All numbers, just like the one above, all numbers is the answer. Because, once again, just like x is always equal to x, similarly, 1 is always equal to 1. So it's not a restriction if you say 1 is equal to 1. Of course it's equal to 1. Okay, so every number satisfies that condition. What about the last one? Nothing, right. So no number satisfies this restriction because 1 is never equal to 0. So that's an empty set. So all the possibilities that you might encounter when you're solving equations. And I picked simple equations, but you can imagine that you're looking at a complicated equation. You don't know what's going to happen at the end, and you don't know what kind of end result you're going to produce. So that is why speaking in terms of sets is so beneficial, because there's always, you know, what's going to, the end result will be very specific. It's got to be a set that contains all possible solutions. So it's possible that you have all numbers. It's possible that you have none. And between all and none, there are infinitely many possibilities as well. Okay, so that is our set building notation and what can happen to it with equations. So this is in particular where set building notations with equations used as the condition. So once again, you have x. Sometimes you point out maybe limit attention x to, say, numbers, real numbers, integers, and so on. You might impose extra restrictions, but these are examples of you have x column, and then you have the restriction. In these examples, all the restrictions are equations. But you can easily think of things that are other than equations. What other restrictions can you impose on numbers to begin with? X. Well, so for example, you can have x is equal to 1. Well, then the answer is equal to 1, right? But you can, how about x is larger than 1? Well, let's say larger than or equal to 1.
1, 2.
1, 2,
1,
so
1, 2,
so it's a whole bunch of them. But it is still, it falls into this category, once again, of set building notation. X followed by a condition that all these x's have to satisfy. So this one is in particular. So the list is, you could write it as a list in this manner. Dot, dot, dot. It is only if we look at integers. If we look at the integers, then we can list them, even though this list is infinite. That's what that indicates. So if we limit ourselves to integers, so x, let me write it out, integers, x integers larger than or equal to 1, the answer is then the set is 1 and everything to the right of it. However, we can ask the same question about reals, the real numbers. So the same restriction, but now we allow all real numbers. So it will be all the fractions, and so it will be not only 1 but also 1.5, and there will be square root of 2 here somewhere, and pi. All of these numbers will be larger than or equal to 1. So that certainly makes things harder because you cannot go one by one verifying the condition. You have to sort of know ahead of time what this means. So any way you can describe this set? It will be 1 to infinity. Well, this is also 1 to infinity, right? So the difference is then you have to either have, well, you just want to visualize it. So let me just visualize it. And we already have a place to visualize numbers. The place is the real line, remember? A line with the origin here, the unit there, and then we just visualize the set on starting with on this location. So this will be its set. The set is this. Everything to the right of 1, including 1, like this. Okay, so that's my set. So say this is kind of set. Say A. This is my set A, with no gaps. You can see the difference from the set I just had above. 1, 2, 3. There are big gaps between it. Here there are no gaps. And so that is you can describe it as array, or a number of ways to describe it. There is also the interval notation for things like this. Have you seen what? Yeah. So how do we do it? This is the notation. You put a bracket, comma, and plus infinity. Okay. So this is what this set is. It's not what this set is. It's rather what I'm giving you is, as I said, the interval notation now. So we have had the list notation for sets. That's the ideal. You just have a list, and you just can go down the list and verify, and you can see every single element in that set. And then, but what if the list is infinite? Not just infinite like that one, but it's really remember, it's not a list by any stretch of imagination, because you can, if you take that set, the green one, and start zooming in on every point, there will be infinitely many points in every single inch. Half inch, quarter inch, we're zooming in, and there are still infinitely many points. So it is not a list. So can't be a list. So that is a discovery in mathematics that was made way later than everything that we have been talking about. So the fact that the real numbers cannot be put on a list. Okay, it's so large that no list will contain it. So that was discovered roughly about, I don't know, 1880 maybe or so. So it's a fairly recent development to realize the different infinities, different sizes of infinities. So one infinity is this one. That's one kind of infinity, and this one is the another kind of infinity. And one is larger than the other. Okay, so the green one is really large, and the other one, the purple one, is kind of a small kind of infinity. Okay. So we're not going to worry about that. We just want to have the interval notation. For what purpose? It is just an abbreviation of the set building notation. So this is set building notation. That works every time. This one, so it's like you pose a question and you have that's just an equality. But on the other hand, you are on the right. It's more compact. And the link to the picture on the right, I hope, is clear, right? So you put a point, or rather number, and then everything to the right is, rather than just writing every number larger than 1, you put it it looks like an interval. Okay, so an interval between two numbers, and except when you use a bracket, it means that 1 is included. 1 is included. Why is it included? Because it satisfies the inequality. 1 is larger than or equal to 1. One of those conditions to be verified, and it is included. So that's why we have a bracket. But infinity is not included. So in contrast, if I pick B, X, once again reals, X strictly larger than 1, then everything is very similar, except now this time the 1 is excluded. So this is how we visualize it. We'll put a number there, and then we'll put a circle there to indicate that 1 is not included. But the rest is the same. So every other number is, if it was in this set, it's still there. Okay, so if this was set A, now I'm looking at set B, and once again 1 is excluded, which means that the internal notation looks slightly different, and that's 1 in plus infinity. I use round parentheses on both sides, and so 1 is excluded. Okay. So once again, strict inequality, strictly larger than 1, means that that endpoint of my array is excluded. Okay. So once again, the connection with the visualization of the set as array is clear. Why do I have a round parenthesis on the right? Why do I not include infinity? There is no stopping point. That's true. But I'm trying to explain the notation, so it would be, it would make sense. So, like I said, exclude bracket, exclude parentheses. So why? And then I choose to exclude from this set A or B. I choose to exclude infinity because why is not infinity part of the set?
Is it because it's not technically like a set number?
It's not a number, that's right. So technically or otherwise, it's truly not a number. It's simply, infinity is not a number, so we will always exclude it. So it's just a convenient location sort of direction in which we're going, but we never reach that point. So think about what set is. Look at the set notation. The set notation is right here, and what it says is all real numbers x that larger than 1. So if it's not a number, it cannot be on the list. Just as well, I could take one of those boys and put it on the list. Even before I start verifying the inequality, it is those boys are not numbers, so they cannot be on the list. And so infinity pretty much serves the same. It takes the same place. It is not a number, so it cannot be on the list of numbers. So that's why it is excluded every time. So never put a bracket where you have infinity, because that would indicate that you have included it. Okay, so more notation of this kind is naturally you can take the opposite inequality, say x less than 3. So it is once again, so set building notation followed by the interval notation, 3 excluded. If I have non-strict inequality, I will include it. Negative infinity 3 bracket. Okay, so that way I have four types of infinite intervals or arrays. So either it goes to the left, all the way to the right, or to the left or to the right. So this one looks like this, from -3 to from 3 to other infinity. So my infinity, positive infinity, still is located to the right. So that's where my x-axis goes. It's the arrow points at the positive infinity, which means that negative infinity is here somewhere. But it's not really a location. It's no more than a direction at which we might proceed. So I'll put it here, negative infinity here, and positive infinity there. But it's really not something that we can ever reach. Okay, and then there is one that came up a minute ago, x, that 1 is equal to 1, say, Okay, so in other words, there is no restriction. How do we write all numbers, all real numbers? It's either negative infinity, positive infinity. So it's the interval runs from all the way from left to right. So it's once again interval notation. And on the other hand, this is the other notation. R stands for the real numbers. Okay, whichever answer is okay. If you are writing a sentence, you can say all real numbers, so that it's okay to use just words. But this is the notation that is appropriate. Okay, now so these are infinite intervals that we have. We have 5. Now finite intervals will be once again. Now let me just make a plot of this. So like this, both of them excluded. One excluded, one included, and both are excluded. Both are included, like this. Okay. An interval, say, from A to B, and then finally, both are included, like this. So this time, neither A nor B is infinite, or infinity, which means that we could include or exclude arbitrarily. Okay, so the notation will be A, B with parentheses, A included, B excluded, A excluded, B included, and both of them are included. So just a compact and geometric way of representing sets of numbers that you encounter a lot. And why do you encounter them a lot? Because of the inequalities. So you solve equations a lot, but you also solve a lot of inequalities. Okay, and in fact, you already see how these inequalities appeared right here, and how they produced those rates. Now I could also write these as inequalities, except there are going to be 2 inequalities. So you limit your progress on one side and on the other side. You have to be very careful about how you do it. So can you express this in terms of what inequalities does have to satisfy? Does X have to satisfy? Yes. In order to be inside of that interval from A to B. I look at the picture. So we include everything. All of this is included, and none outside is included. So how do I algebraically now, using the set building notation, express this set? X. Well, what is the relation of X to A?
A is less than X, which is less than B.
That's right. Like this. Okay, so like I said, it's 2 inequalities. 2 inequalities that have to be satisfied. Just in case if you haven't seen before, like a double inequality, that's what it is. This is what it means. That such an inequality means that X is larger than A, and X is less than B. Okay, so in other words, what I'm saying here is that my condition has 2 parts, and both of them have to be satisfied. So that's the important word "and." It has to be satisfied in order for X to be in this set. So if X is simultaneously larger than A and less than B, then we have this interval. So the difference over here will be that just the inequalities will be strict or non-strict. So the second line, A is less than or equal to X, strictly less than B. Okay. The third one, X, A is strictly less than X, and then it is less than or equal to B. And finally, we have both non-strict inequalities in the last line. Okay, so I think the notation makes sense. So if you just remember that it has to do simultaneously with what's on the left and on what's on the right. So on the left is the geometry or visualization of your numbers, It is a set of numbers, and this is set building notation is on the right. So then my interval notation is reflects simultaneously both of them. What's happening on the left, the geometry. So between A and B, every time it is something that lies between A and B, and one of those might be infinity. Okay, and then this is the set. Also, never forget that this is a very good thing to use is the set building notation, which is on the right. Okay, so there is something else that I want to mention, and that is a visualization of numbers in addition to what we just did. So this is the basic visualization of numbers is units, okay, -1, 0, 1, 2, 3. So these are the integers to begin with, and then the assumption is that there are more numbers in between, all the halves and quarters and thirds, and as well as a whole bunch of irrational numbers are all here. But even if you just look at the integers, there is another way to visualize it, and that is colors. So colors are encoded with numbers. Okay, in case you haven't seen this, here it is. You see it? So I opened this dialog box, which is edit colors, and you can pick different numbers with different colors. They are characterized by by a combination of 3 numbers. Okay, so as you can see, that's what's on the right. We're looking at color, which is looks like almost black, and it is associated with a combination of 3 basic colors, and those are on the right, red, green, and blue. Okay, so we'll do one at a time, and in particular, let me show you how I can move this color and what's happening to. When all these numbers are zeros, that's when you have a black. If I go all the way to white, all the numbers become 253, 254, 255. So the numbers run between 0 and 255. Okay, so once again, 0 is black, 255 is white, and then everything in between. So I could have any number here. As you can see, gray. The numbers increase and decrease, 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 and at some point it looks totally black, but actually it has 17 steps above it. Okay, so that's the correspondence. That's how every single image, as far as I can tell, is encoded as that you see on the screen. Where colors are encoded in that manner. But what really is how you can utilize this is to see it with Excel. So there is an option of coloring of what is called. It is called. Okay, where is it? Conditional formatting. Okay, so for example, I could choose a bunch of numbers. So let me give you maybe 20 numbers here. So starting with 0. And this is, I'll progress one at a time, like this. So I have a bunch of numbers like this. And then I could color them according to these numbers. Okay? So, like I said, this is called conditional formatting. And I could color them. I could color them with different color scales. So one way to color such a scale is the one that I just showed you. From white to black, so that's kind of an easy one. But the Excel has more fancy ways to do it, and that is this. For example, it can run from blue to red. In fact, let me make that point here. What if I put here -10? Okay, so roughly speaking, what you're looking at, how you can colorize numbers is negative numbers are blue and positive numbers are red. Okay, so there you go. That is the that's sometimes you see that when you see, say, a temperature map, and it puts appropriate color at every location on the map, and that color indicates how hot that spot is. Okay. Okay, so we'll just resume next week. Bye.